Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine standing on the banks of the Thames in London during the summer of 1816. Instead of the typical gray drizzle, the sky is a riot of unnatural colors. The sun doesn't simply set. It dissolves into a bruised palette of violent oranges, lurid purples, and an eerie, metallic yellow that seems to hang in the air long after the light should have faded. While contemporary observers found these displays hauntingly beautiful, they were witnessing the chemical aftermath of a geological catastrophe thousands of miles away. Today, atmospheric scientists are looking back at the masterpieces of the 19th century not just for their aesthetic value, but as high-fidelity records of stratospheric chemistry. The primary driver of these spectacular skies was Mount Tambora in Indonesia, which erupted in 1815. It was the most powerful volcanic eruption in recorded human history, ejecting so much material into the atmosphere that 1816 became known as the year without a summer. But the visible ash that fell near the volcano was only part of the story. The real global impact came from the millions of tons of sulfur dioxide gas blasted directly into the stratosphere. Once there, this gas reacted with water vapor to form tiny droplets of sulfuric acid, known as aerosols. Unlike heavy ash that falls back to Earth quickly, these microscopic aerosols can remain suspended for years, hitching a ride on high-altitude winds to encircle the entire globe. This is where art history meets atmospheric physics. These stratospheric aerosols act as powerful scatterers of light. Specifically, they trigger a phenomenon known as Mie scattering. While the normal blue sky is the result of Rayleigh scattering, where smaller gas molecules scatter shorter wavelengths of light, the larger volcanic aerosols preferentially scatter longer wavelengths. This shifts the spectrum of the sunset toward the deep reds and oranges. The more aerosols present in the stratosphere, the more intense and varied these colors become. Enter Joseph Mallard William Turner, the legendary British painter often called the Painter of Light. Turner was an obsessive observer of the sky, and his career perfectly overlapped with several major volcanic events, including Tambora and the later eruption of Babuyan Claro. Art historians have long noted a dramatic shift in Turner's palette during these years. His skies became more opaque, his oranges more acidic, and his horizons more diffused. For a long time, this was dismissed as a stylistic evolution toward Impressionism. However, modern researchers have found that Turner wasn't just being creative, he was being an accidental chronologist of climate change. In 2014, a landmark study led by the Academy of Athens analyzed hundreds of sunset paintings created between 1500 and 1900. By using digital image processing, the team calculated the ratio of red to green light along the horizons of these artworks. Because volcanic aerosols increase the redness of a sunset, this ratio serves as a proxy for aerosol optical depth, a standard scientific measure of how much light is blocked or scattered by the atmosphere. When the researchers plotted these color ratios on a timeline, they found a startling correlation. The peaks in redness in the paintings aligned almost perfectly with the dates of major volcanic eruptions recorded in ice cores and historical chronicles. This scientific validation extends beyond Turner. Consider Edvard Munch's iconic The Screen. While painted in 1893, many scholars believe the terrifying, wavy red sky in the background was inspired by Munch's memory of the 1883 eruption of Krakatoa. That eruption sent a pressure wave around the world 7 times and tinted skies globally for nearly a decade. Munch described the experience in his diary, noting that the clouds turned as red as blood, and he felt a great, unending scream piercing through nature. What he was describing was the physical sensation of witnessing a high-altitude chemical reaction on a planetary scale. By treating these paintings as data points, scientists can fill in the gaps in our historical climate record. Before the era of satellites and high-altitude weather balloons, we had very few ways to measure the composition of the upper atmosphere. These 19th-century masters, with their dedication to capturing the exact nuance of a sunset, effectively acted as global sensors. Their brushes recorded the concentration of sulfuric acid in the stratosphere long before we had the vocabulary to describe it. It is a profound reminder that art and science are not separate silos, but different ways of documenting the same objective reality. The next time you look at a vibrant sunset in a museum, you might not just be looking at a beautiful landscape. You might be looking at the chemical signature of a world in flux. For more incredible facts like this, don't forget to subscribe and turn on notifications.